Group and has been at Alamos for 23 years. During that time, he has performed nuclear design for very small reactor systems and safety analysis for a variety of reactor concepts, with an emphasis on severe nuclear accidents like 3 Mile Island and Fukushima. Patrick got his start with a BS from the University of Oklahoma and an MS from the University of New Mexico. And I know that some of these projects have very interesting names derived from The Simpsons. Yes, there was a project called Homer, and you can ask him about other names as well. So please now, welcome Patrick McClure. Why don't you get seated and we'll make
Sure.
all happy for you. All right.
Yeah, we keep track of my 15 minutes. All right, can you all hear me?
All right.
Well, thanks for letting me come and speak. Again, I am Pat McClure. I've been at the lab now almost 24 years. Almost all of that over doing things related to nuclear reactors. So what I want to talk to you about is KiloPower. KiloPower is a small space reactor. And it varies. At the low end, we have a version of it that we're testing. It produces about a kilowatt of power. A kilowatt is about enough energy to power your toaster. We also have a version that goes up, same reactor, but we can scale it up just ever so slightly. It'll make 10 kilowatts of power. That's enough to power 2 or 3 houses. So if we had it on your block, we could actually power you and a few of your neighbors. So the first question usually people want to know is, why is NASA so interested in space, nuclear power for space? Well, the answer is pretty simple. If you're close to the Earth, solar is wonderful. It provides you all the power you need. But as you start to move out into deep space, you get further from the sun, the amount of energy becomes a lot less, and it becomes much more difficult. So once you're out past Mars, really solar is pretty tough to do. So for the past 20 or 30 years, we've relied on what's known as radioisotope power, which, by the way, is also on the planet. And with radioisotope power, we can provide several hundred watts to spacecraft or to robotic landers that we put on Mars and other things. The reason for doing a small reactor is we want to grow things, is we want to do more, bigger missions out into the solar system. We're going to need more power. Also, if we try to actually colonize Mars or maybe put people on the moon, we're going to need more power. So that's why NASA cares about it. So the reactors we talk about are not very big. So let me give you an idea for size. The reactor core we're talking about is about the size of a Quaker oatmeal box that you grew up with. Once you put all the reflector and shielding around it, that makes it about the size of a trash can. And its biggest, it's about as tall as a small step ladder. So that gives you an idea for size. It's actually fairly simple. It has really 7 components to it. It's got a reactor core that is a solid block. It's actually a solid cylinder of uranium. That is surrounded by a neutron reflector. What the neutron reflector does is as neutrons leak out of the core, this reflects them back in so we conserve them. That means we need less nuclear material to get a critical mass. That's made out of beryllium oxide, which is a ceramic. We have one piece of control on the reactor, and I'll explain more about that in a minute. We actually have a boron carbide rod that's a neutron absorber that turns the reactor on and on. It actually does not control the reactor. We actually use regular nuclear physics to control the power of the reactor. And I'll explain that a little bit later. That's the core. That's how it turns on and off. How do we get the heat out? Well, we have heat pipes. Heat pipes were invented at Los Alamos in 1963. Actually, it's part of the rover program, which is where we were doing thermonuclear rockets. So heat pipes are simple tubes. They have a liquid in them that boils at one end. It travels at the speed of sound to the very other end, where it condenses and deposits its energy. And then the fluid is returned to the bottom via wick. Much like a paper towel or a stem might move fluid. So that's how we deliver heat from the reactor to our power conversion. Our power conversion is actually another simple device. It's called the Stirling engine. There was a gentleman, his name, I gotta get his name right, but his name was Stirling. He was a minister in Scotland, and in the 1700s he invented a heat engine called the Stirling engine. It works off a simple temperature difference. If you have something really hot and you have something really cold, that engine will actually take those two heat and actually move a piston, which then can be used to drive an alternator and make electricity. So in our case, the reactor delivers heat to the Stirling engine through these heat pipes. The Stirling engines make electricity. And how we keep them cool is we have some aluminum radiator panels, which also have heat pipes that will carry the excess heat away. And that is all this little reactor is composed of, is those 7 pieces. So right now, we've been developing this little reactor for about 5 years. We started off with some LDRD money, and we got to do a small experiment to demonstrate the physics. We actually took an existing small reactor. It's actually a unit called Flat Top. It used to live here at Los Alamos, now lives in Nevada. It has a 17 kilogram spherical core of uranium. We put a heat pipe in it, and we made it go critical and showed that we could power a Stirling engine. And that was done in 2012, and that got NASA excited enough that we got a second project. And that project was to actually build this small reactor, a 1 kilowatt version of this small space reactor KiloPower. We are calling that test KRUSTY for kilowatt reactor using Stirling technology. If you don't get the references, our chief reactor designer Dave Poston is a big Simpsons fan, so all of his tools, all of our experiments are named after Simpsons stuff. So, with the completion of DUFF, we're just about to finish KRUSTY up. Matter of fact, just to let you guys know, because one of my bosses is here and he knows, I'm actually headed to the test site tomorrow at our 5:30 flight, our final test, running the reactor at its peak temperature and full power for 28 hours is going to occur Tuesday and Wednesday. And that will finish up this portion